So we have discussed few concepts such as instrumentation amplifier in a previous lectures, right, where we had multiple stages and how we connected them, and how we actually saw that ACL is a multiplication of stage 1 and stage 2, right? So we started off with a small circuit, right, where it had a differential input, and we also used a difference amplifier, right? So we started combining them, and then we had a common potential given, right? And that was called common source, right? And yeah, we came up with a circuit, a complete circuit called instrumentation amplifier. So today, we will shift our focus to precision rectifiers, right? So these are also this is also an interesting concept where we will be looking into, how these rectifiers, or how with the help of op-amp, how things can change, right? Okay, so the use of op-amps can improve the performance of a wide variety of signal processing units. So whatever signal that we're getting, we need to process them in order to enhance its usability, right? So if I'm just getting a raw data, let's say for example, right, you are capturing photos on your digital camera. So before you take those information, right, you need to connect it to your, say, desktop or probably your laptop, and probably you need to do some processing on the images, probably you need to do some rendering, right, on the video. So there are some kind of processing that needs to be done before we proceed with things, right? So that is nothing but called signal processing. So all this happens with the help of electronics, right? So op-amp has really played a very major role, right, in the field of electronics, where it can actually work as a divider, it can work as a multiplier, right, and it can also be modified. We can change the gain, right? So many things as that sort. So rectifier circuits, you would have seen, right, full wave rectifier, half wave rectifier, right, a bridge rectifier. So these are all done with the help of diodes, right? You would have seen that in your labs. So rectifier circuits, the voltage drop that occurs with an ordinary semiconductor rectifier can be eliminated to give precision rectification, right? So we will use an ordinary semiconductor, okay, and this can be used to eliminate, or to give more precision, which means accurate rectification. Waveforms can be limited and clamped at precise levels, so you don't have to wait for the waveform to go too high, if you want to limit it to a particular level, right? So that is possible, with the help of op-amp. So clipping and clamping circuits, so these are going to be the application of these precision rectifiers. So the errors that occur with peak detectors and sample and hold circuits can be minimized by using op-amp. So whatever errors that were seen previously because of the inaccurate rectification, all that can be modified with the help of op-amp. Right. So this is a simple circuit that you can see here, where it is connected to a diode, okay, a normal diode, and once you give the input, right, Vi, and then it's with respect to ground, okay, at the positive. So you should be able to see a non-inverted form. So which means if it's at the positive side, you should be able to see at the output also the positive cycle, right? So the circuit of op-amp of precision half-wave rectifier is illustrated here. Okay, it is nothing but a voltage follower with a diode inserted, right? So we all know that in the reverse bias the diode doesn't conduct. So taking that property, we can actually just make sure that the negative part of the waveform is clipped off. So once we insert the op-amp output terminal, okay, the diode, the circuit output point, the signal input is positive, the diode is forward biased, right? So that's the beauty of having a diode, right? So we are making the use of the property of this diode where it works when it's forward biased. Okay. And the voltage follows the input, okay, and negative feedback causes the voltage at the inverting input terminal to follow that of the non-inverting terminal. Since the output of the circuit and inverting terminal are common, the output follows the input with microvolts. The diode forward voltage drop is not involved. So whatever that you see here, right, the potential that you see at the positive terminal, at the negative terminal, they try to equate with each other, right? So if I have +5 here, also it tries to be +5. If it's -5, it tries to be -5 here, right? So they try to equate themselves between the two terminals. So this is possible, only with the use of an op-amp. So when it's negative, so ultimately we know that this will get into a reverse bias. So when it's in reverse bias, we do not find that it is conducting. When the input voltage is a negative half cycle, right, the op-amp output is negative and the diode is reverse bias. So an important concept, right, which is used, an important property which is actually used for the purpose of rectification. Okay, so rectification previously was done only with the help of diodes, but then now we are taking the help of op-amp also, because we need precision. Precision means accuracy. Consequently, the feedback path is interrupted. So there's no any feedback path here. So which means I can say, that this feedback path is as good as not having it. Okay, not having. So the feedback path is interrupted and the inverting input terminal remains at ground level. Okay, so this will remain at ground level because RL is grounded. So here RL is grounded and the op-amp output is saturated in negative direction. So once it gets into negative direction, we know what happens with the diode. The negative half cycle of the input does not pass to the output. So it's like blocking, right? So it's blocked. And ultimately, whatever is in the input should actually appear at the output. So this negative part is not appearing at the input. So which means there is nothing at the output side. So these sections are nullified. Okay. Consequently, the feedback path is interrupted and the op-amp output is saturated in negative direction. The negative half cycle of the input does not pass and it is clipped off. So the output waveform is half-wave rectified portion of the input. So whatever input that you see, okay, the negative portions are taken off. Okay, and that is passed on, and you can find at the output only positive cycles. Fine. So next, we will now look at the figure B. Okay, so we will concentrate now on figure B, and we will see what exactly we are going to learn from it. Okay. So there are small changes that you can see in this figure, right? So the diode is remaining the same. We have the same op-amp, which is connected to plus VCC minus VI is given here. Diode is also there, right? RL is also there. But one interesting inclusion that's happening here is R1 and R2, right? So R1 and R2 are brought in and it is inserted as compared to our previous circuit, right? So with this we will see that the waveform amplification has changed. So if I can change the value of both R1 and R2, right, this waveform amplitude can also be changed, right? So let us look into it in detail. So figure shows the circuit of precision rectifier with voltage gain. So not only rectification, But then here I'm able to achieve gain. So how is this gain? Gain is in the form of amplification. This this waveform will have its own amplitude and which is variable, right? So how is it variable? Based on my selection of R1 and R2. The circuit is designed exactly as non-inverting amplifier, so which means there is no phase shift, 180-degree phase shift, except the current through R1 and R2 should not be less than 100 microamps. So there's a threshold here, right? So the threshold is about 100 microamps. Okay. So it should not be below that, but then it should be above. To ensure that the diode is operating correctly in the absence of load current. So if we have to ensure that this diode has to operate properly, we need to give some food to the diode, right? So that food is in the form of current, and it should not be less than 100 microamps. A minimum diode current of 500 microamps is a good design objective. So if I can have probably 500 microamps in mind with respect to diode, then that becomes good. Now there are few advantages. Okay, now I could ask few questions. What are the advantages of these precision rectifiers over the simple diode that we were using previously? Okay, so these 4 points can be your answer. Okay. So what are they? No diode voltage drop between input and output. Okay, the ability to rectify very small voltages. So that's why it's called precision, very accurate. And also there is no diode voltage drop. So diode does not cause any drop in its voltage between input and output because of the op-amp, because op-amp helps in maintaining that, in regulating that. Okay, because of the gain of the op-amp, the ability to rectify small changes. Okay, so much smaller than the typical 0.7 volt diode forward voltage drop. So this can even sense about even 0.7 volts. Amplification can be done if needed, like how we are seeing it here. Okay, and it has low output impedance. Okay, infinite input impedance. Okay, and very low output impedance. So this is the property of an op-amp. So that's when you try to combine two things, an op-amp, okay, a diode. So diode was previously used exclusively for rectification, but then right now you are combining it with op-amp. Okay, so 1 and 2 indicate that precision rectifier is close approximation to an ideal diode. So with 1 and 2, we see that it's becoming more accurate. Okay, so not only rectifying, but then it's very accurate. While the input waveform in its negative half cycle, the output of op-amps in the figures are saturated in negative direction. Some time is required to get the op-amp out of saturation, and this will limit the frequency response of the circuit. For high frequency performance, a non-saturating precision rectifier can be used. So these are actually used for low frequency operations. If I have to use high frequency, then I will have to use a non-saturating precision rectifier, because that will make it faster. This setup here that we are seeing is not as fast as the setup that we are going to see next. Okay, so these are actually only saturating precision rectifier. Okay, so these are a little slow. Okay, and it cannot be used for higher frequencies. Okay, so you can see here we are including a diode at the output voltage follower, or a non-inverting amplifier that converts the circuit to a precision half-wave rectifier. So diode in combination with op-amp makes it precision. Only the positive half cycles of the input are passed to the output, and there is no diode forward voltage drop between input and output. So that's the specialty of having an op-amp and diode combination. So for higher frequencies, we cannot use saturating, okay, because it needs to be faster. These are not faster, right? So So we can change the way that op-amp acts based on what devices are connected. Okay. Another important point is, there is some time which is needed to get the op-amp out of saturation, and this will limit the frequency response. So with this setup, the time taken for this op-amp to move from one mode to another mode, right, from getting it out of saturation mode, is a little time consuming. So we will not be using this for higher frequencies, okay, but instead we will use the other setup which I'm going to show now, right? So here you can see we are using two diodes, right? And R1 has moved here to the input side, okay, and R2 is in the feedback line. Okay, so pretty same, right? We're using pretty same, but then previously how many we had? Only 1, 2, 3 resistors, right? And here also we are having 3, but then one extra thing that we're going to see is with the feedback link, okay, with the feedback line. So R1 is at the input side, R3 is at the non-inverting terminal. Okay, then you have a diode which is connecting from the negative terminal to the feedback, right? And also you have a resistor doing that work. Okay, so basically you have a diode and a resistor in the feedback network, and RL as usual is the load. Okay. So here now you can see, this is an inverting configuration, right? Where the reverse happens, the positive cycle is clipped off, and we just retain the negative cycle. And since there's a phase shift of 180 degree, so we can see that the waveform is appearing in this format. So we have an important formula here, right? V naught is equal to minus Vi R2 by R1. So this formula, probably you can make a note of it. Okay. V naught is equal to minus Vi R2 by R1. The precision rectifier in the figure uses an inverting amplifier configuration. Why is it inverting? Because inputs are given to the negative terminal, right? Then diode D1 is reverse biased and diode D2 is forward biased when the op-amp output terminal is positive. So these two are working differently. Okay, when one is reverse, the other is forward, the other is forward, the other diode is reverse biased. So we know in reverse it doesn't conduct. Okay. This occurs when the input signal is negative. Okay. While D2 is forward biased, okay, when this D2 is forward biased, we have the output equation. Now we cannot afford to make this D2 in reverse bias. Why is it so? We wouldn't get even these waveforms, right? Okay. Now let's say, for example, this R2, okay, this R2 is equal to R1. Okay, R2 equals R1, then V naught is equal to minus Vi. So if I have these two, if R2 and R1 both are same, both the numerator and denominator will get cancelled. So I am remaining with only minus Vi. So there's a kind of small trial and error method here that we can do in order to get a proper waveform. Okay. If R2 is greater than R1, now we have a condition here. If it is greater, okay, if this feedback resistor is greater, the output is an amplified version of input. So if and only if it is greater. If it is less than this, then it's not going to amplify, right? Because there's no point in having this resistor if it's less than 1 kilo ohms, right? So we will have it greater, and there's a amplification that happens. Okay, so that's the condition. The next that we'll be looking into is how it actually operates. Okay, how this non-saturating precision rectifier operates. So during the positive half cycle of the input, the op-amp output terminal goes negative, right? Because it is in the inverting format, right? Inverting format. So of course it goes into negative, causing D2 to be reverse biased. So D2 will be in reverse biased, right? So it's not going to function. Without D1 in the circuit, the op-amp output would be saturated in negative direction. So it will be saturated. It will always be in the negative direction. Right? However, the negative voltage at the op-amp output forward biases D1. So if I have a negative voltage here, right? So that is going to forward bias negative voltage here, right? So that is going to forward bias my diode D1. So when it's forward bias, that means it is functional. Okay. This tends to pull the op-amp inverting input terminal in negative direction. So previously, we were not able to do that, but then now with this additional setup of D1 and D2, we are able to achieve this, bringing the op-amp into the negative point. Pull the op-amp inverting input terminal in negative direction. But such a move would cause the op-amp output to go positive, right? So if it goes positive, right, so the reverse is going to happen. So the output settles at the voltage that keeps the inverting input terminal close to ground level, right? So here you can see that the positive terminal here is connected to ground via resistance R3, via resistance R3. So if we have to do this, right? If we have to do this, having it in negative, connecting it to ground potential, then this negative terminal also will try to maintain as much as possible the ground potential. So in this case, the voltage at diode forward voltage drop below ground approximately minus 0.7. The sole purpose of D1 is to keep the op-amp output from going into saturation. So with the help of this D1, it will make sure that it doesn't go too negative, but then it just stays there, so that immediately I can bring it back from the negative point. So because of this, what is happening is I can make it go into positive and probably into the ground level for a certain time. Okay, so the switching happens faster. So switching means frequency, right? So higher frequency of pressure. So to keep the op-amp output from going into saturation and thus maintain a good frequency response. So because of that, what is going to happen? This D1 will make sure that the op-amp will be operated or can be operated at higher frequency. Okay. So the inverting circuit is converted into non-saturating precision half-wave rectifier circuit, and by the inclusion of two diodes D1 and D2, when D2 is reversed, then D1 provides negative feedback to keep the op-amp output from saturating. Now, because of this, setup, right? Because of this setup, we can have the negative feedback, and that is done with the help of diode D1. Because if I give a positive feedback, what is going to happen? There is going to be a lot of oscillations, and I do not want that to happen, right? I want minimal oscillations, and I want to make sure that my output is as stable as possible. So the best bet for me is to have a negative feedback, and that is done through the help of diode D1. So let us discuss today. Okay. Now, continuing the discussion with the negative cycle. Okay, so we have seen what happens in the positive cycle. So the reverse happens in the negative cycle of input. So where D2 goes into off mode and D1 gets into on mode. So in the negative half cycle of the input is inverted and passed to the output, while the positive half cycle is clipped off. So this cycle, this waveform that you see is clipped off. Okay, so only the negative part is coming. If the polarity of the two diodes are reversed, then the negative half cycle will be clipped. So let's say I make this reverse connection, okay, and also I convert this into reverse. So in that case, the negative part of the waveform is going to be clipped off. Okay. And the positive half cycle will be inverted and reproduced at the output. So here this positive cycle will be inverted, and I'm going to get something, probably like this. Okay. I'm going to get like this, and we wouldn't probably have these. Okay, if in case the diodes are reversed. Okay, so inverse things are going to happen. Okay. So design of non-saturating precision rectifier involves design of inverting amplifier. Okay. The diode should have minimum reverse voltage greater than the supply voltage. So that's a small condition here, right, where the diode should have a minimum reverse voltage, okay, which is greater than supply voltage. Reverse voltage greater than supply voltage. They should also have a switching time that will not limit the circuit frequency response. So not only having this kind of setup, but then I need to have these diodes also to work fast. So if diodes don't work fast, my frequency or my switching operation is not going to happen. So ultimately, the operation of frequency is going to be limited, and it's going to be a low frequency operation. Okay. So they should also have a switching time that will not limit the response time. This requires the diode reverse recovery time be much smaller than the time period of the highest signal frequency to be processed. So this diode, getting into forward bias, reverse bias. So this kind of switching should be faster, because there is 100% feedback when D1 is forward biased, right? So you can see that because of this forward bias condition, so you can have a negative feedback connection. The op-amp should be compensated as a voltage follower. Why is it a voltage follower? Because whatever is at the input, the same thing appears at your output. So now we'll try to solve one example, right, with regards to non-saturating precision rectifier, and we are going to use the same circuit that we used previously, right? R1 being 1K and R2, right? R3. So we will see how these problems are solved. Design a non-saturating precision half-wave rectifier to produce a 2-volt peak-to-peak. Okay, so when it is peak-to-peak from one peak to another peak, it should be 2 volts. And the frequency is 1 megahertz, and we're going to use a sine wave for that with 0.5 volt peak value. Okay, 0.5 volt peak value. Use a bipolar op-amp with a supply voltage of plus 15. Right. So we are going to use plus or minus 15, plus 15 minus 15. Okay. So as usual, what we do is we select I1 is equal to 500 microamps, right? For that's the minimum requirement for a diode. Okay. If we can maintain at about 100 micro, that is the threshold, right? But if for proper operation, right, for proper operation, if we can maintain I1 to be 500 micro, then both the diodes would work, in a proper way. So if I have to calculate the R1 is equal to, right, V1 by I1. So V1 here we have 0.5 divided by 500. So that's going to give me 1K. So initially, we don't have these values, right? We don't have these values, and then we will start finding out one by one. So R1 becomes 1K, right? And of course, this is a standard value, and we can use a diode for that. Similarly, now R2, let's calculate how R2 comes. So we know that the output voltage should be 2 volt peak to peak, right? And I1 we have, of course, 500 micro. So when we do a quick division, we will be getting about 4 K. Can someone confirm if we are getting the same value about 4K? Please check. Two divided by 500 micro. Yes, are we getting 4K? Yeah. Okay. Fine. So we will be getting about 4K. So we will use 3.9 as the standard value. Okay. If not, then we can also use 1K in series 4 times, right? So that's going to be a little difficult. So instead we will just reduce the resistance to a little level, okay, and we'll use 3.9 for that. And R3, you can see here R3, okay, R3 is equal to R1 in parallel combination with R2, R1, R2. So 1K, I have 1K and R2 is 3.9. So if I take both of them, right, R1, R2 divided by R1 plus R2, I should be getting about 796 kilowatts. 796 ohms. Okay, so we will be using standard 820 ohm resistance. Okay, so this should be ohms actually. For diodes D1 and D2, okay, there's a small condition here that we're going to follow, right? So VR, okay, VR should be greater than VCC minus of minus VEE, and that should be greater than 15 volts minus of minus 15. So plus 15, okay, minus of minus 15. So this is a condition, okay, that we need to follow for diode. So as of now, you don't get confused with these conditions, because these conditions are kept so that the switching frequencies are faster and the response times are good. Okay, so you need to remember that it should be greater than VCC, okay, minus of minus V. So VCC minus of minus becomes plus. Okay, so that should be at least greater than 30 volts. Okay, the voltage across R. Then the rise time, remember I told you the switching time between forward biased and reverse biased, right? So we should be taking about 0.1 times of T. So 0.1, 1 by F is nothing but T. So 0.1 divided by 1 megahertz. So we should be having the response time of about 0.1 microseconds. Okay. So this is how these circuits are designed, and diodes are selected, okay, so that the negative feedback keeps going. Okay. Fine. Now two output. Okay, so we will have two kinds of outputs. Previously we just saw one kind of output, right? Only one output. So now it is two output half-wave rectifier. Okay, so we will see how this works. So we're going to have the same setup, but then instead of having a negative feedback here like this, right? So what am I doing? I am having a diode here and the resistor, okay, together. It's not like a parallel combination, okay, but then it becomes a serial combination here. Okay, so with this, we'll see how it's going to function with this kind of combination. So let's look into the operation. Although the precision rectifier, okay, which was mentioned in this figure, has two outputs, terminals, it is just modification of the circuit of 9.2. So the previous circuit, right? So which means slight changes, as I mentioned. So instead of having it here, connected, we are shifting that diode here. Okay. And we are having R4 here, R3, right? So this R2 is remaining the same, R1 also is the same, D1, R2, right? So diode and resistance, then that positive terminal and I have R3, right? I have R2 at positive terminal, right? Only thing is, we don't have an RL here, so instead of RL, I'm using R4. R4, yeah. So that's about it. Fine. So it is a modification. Diode D2 is connected in series with the op-amp output terminal. So you can see that diode and this resistor are in a series combination, and with the help of D2 R2, I'm going to get VA, that is my first output, and with the help of D1 R4, I'm going to get the second output, which is PV. So here the speciality is I'm going to combine the properties of them, and positive is of course inverted, remember, because we are having an inverting configuration here, and if we want, we can just take the negative cycle here, or we can take the so it's like separating the waveforms, right? Inversion and separation. Okay, so D2 is connected in series, and the resistor R2 exactly. Okay, so D2 and R2. So D1 is also connected like previously, except that R4 has been added in series with D1. So R4 and D1 are also in series. So during the positive half cycle, now let us see the operation, how it works. Now let us say the waveform has started. Okay, it has come in its positive form. Okay, the op-amp output terminal goes negative, right? Because it's a non-inverting form. So whenever it's positive here, the output goes negative. Now, which one is going to be reverse biased, which one is going to be forward biased is what we're going to look into, right? Okay, so this is going to cause D1 to be forward biased. So D1 is going to be forward biased. So I'm going to give a negative potential here, okay, and positive, I'm going to get it from the other way around, right? Positive, I'm going to get it from here. I hope you're able to follow, right? Let me just annotate. Okay, so let's say I'm giving a positive potential here. Okay, so this will come here, come here. Okay, so this is having positive here. Okay, just use another form. So this is going to be connected to the positive side, and the output is going to be negative, right? So which means D1 is what? D1 is in forward bias, right? And D2 is in reverse bias, because negative terminal positive is connected here and negative is connected here. So D2 is in reverse bias. So D1 is forward biased and D2 is reverse bias. So reverse bias means this is not going to work, right? It's going to be cut off, and my feedback is ultimately cut off. So in this situation, the op-amp together with resistors R1 and R4 functions as an inverting amplifier to give the output at B. So at this point of time, I will get only the output from B. Here I'm not going to get, because the diode is not functioning. D2 itself is not functioning, right? So what is going to be my formula for that? It's going to be VB is equal to voltage at point B is equal to VI, the input voltage, into minus R4 by R1, because R4 is involved here. R2 and D2 is not involved. Okay, So no current flows in resistor R2, and at this time, because D2 is reverse bias, so we saw here minus and then here plus to the anode and cathode, right? So yeah, also R2 is connected to the virtual ground at the inverting input terminal. Now since we have this positive terminal connected to ground via resistance R3, so this will also be in the virtual ground concept. Okay. So the output at a point A remains at ground level for the duration of input positive half cycle. Okay. So during the positive half cycle, we don't have an output at point A. So when the input is in negative half cycle, the reverse happens. This gets into you know, reverse bias, right? So this gets into reverse bias. So we will be having only D2. So which means we are not going to get VB. We'll be getting only VA, and D2 is forward biased. Okay. And we're going to have combination with R2 and R1. So here you can see instead of R4, it's been replaced with R2. So minus R2 by R1 is going to be your formula now. Okay. At VB, at VA, minus R2 by R1. So D1 is reversed, no current flows in resistor R4, right? So which means, you know, this whole line is as sort of not connected. Okay, and it's at virtual ground concept, and terminal B is 0. Okay, it is seen that this precision rectifier with positive half cycle of terminal A and negative half cycles at terminal B. So at terminal B, I'm going to get negative cycles. Okay, and at terminal A, right, I'm going to get the positive cycles. So this is the waveform. So I hope you have understood. So with the help of diode, you know, it becomes so simple, right, to just cut off the operation, cut off the waveform, and we can try to split them into different waves. Okay. Now we will see this half-wave rectifier. Okay, half-wave rectification and summing circuit. Okay. So here it's a combination of both. Right? So we can see previously we didn't have this kind of D2, but then here D2 and D1 are, you know, changed the way that they are connected. Okay, so let's see here. Yeah, so you can see in this non-saturating format. Okay, the anode and cathode. The anode is connected to the output of op-amp, and you know, the cathode, you know, is actually connected to the output, you know, or you can say to RF, right? So the way in which D1 and D2 are connected is actually reversed here with this half-wave rectifier and summing circuit. You can see that, you know, D1 and D2 are connected in the reverse format. So there are two sections here. The first one is going to be the precision rectifier, and the other one is going to be the summer. Summer we have seen, right? So what is going to happen? We will get the sum of two or more inputs. So basically it's the sum of inputs. So we have seen summer, you know, differentiator, integrator. Okay, so those configurations are taken here in combination with precision rectifier. So it becomes a new hybrid circuit. Okay, and we can call it as precision full wave rectifiers. Fine. So the left side of the circuit is a precision half-wave rectifier, okay, just like we have seen previously, but the diodes are reversed. Only that. Apart from that, it's all the same. And similarly, we have the point A and point B here. Okay. The input voltage is applied to terminal A of the summing amplifier. So A resistance, it goes to the non-inverting terminal. And this one also has a negative feedback with the help of R6. Okay, and as usual, I have R1, okay, R7 here, okay, for the non-inverting terminal connected to ground via R7, right? Okay, fine. So note that the resistor R2 in precision half-wave rectifier circuit has twice the resistance of R1. Now, can someone tell me why we are trying to do this? Why we are trying to increase the resistance of R2 compared to R1? Is there a specific reason for that? Yes, can someone tell me why are we trying to do that? We have learned it, right? We have learned it as to why this resistance value is taken higher compared to R1. Why R2 is higher than R1? Yes, Vikram, go on. Go on.
So that there is amplification.
Very good. So that we can maintain amplification. So if in case this resistance is too small, then the whole purpose of amplification is not going to happen. So that's the reason, I should be having greater than R1. So here I'm going to take about 2 types of R1. Good. Okay. So one of the inputs, is going here, and the output of the op-amp, that is point P, okay, is also connected, and that is via R5. You can see that, there is a kind of similarity between both, right? The positive terminal is grounded via resistance, and here also grounded via resistance R5. Okay, so the input is applied, and R2 in the precision half-wave rectifier circuit has twice the value of R1. So the rectified voltage applied to terminal B, okay, in the amplifier is minus 2 times of VI. Okay, so 2 times of VI. As you can see, right, it is doing the amplification, and this amplification is with the help of resistance R2. So hence it is 2 times VI. If you make it 3, then it becomes 3 times VI. Okay, so during the positive half of the cycle, okay, the voltage at terminal A is plus. Okay, so during the positive half of the cycle, okay, you can see that there is an inversion happening here. Okay, why is an inversion? Because it's connected to negative terminal, and because of 2 times R1, instead of having the same VI, I am having 2 times of VI. Okay, and that way in negative direction. Okay, fine. The output from the summing circuit with R5 is equal to R4. So R5 here is equal to R4. So we will come out with an equation, okay, where V0 is equal to minus R6. Okay, the final V0, the output here, okay, is equal to R6, that is the feedback, minus R6 by R4, R6 by R4, and the input voltages are added, so VA and VB both are added and then sent, right? So which means it is equal to minus R6 by R4 VA is nothing but VI, okay, minus 2 times of plus of minus 2 VI. Okay, so it becomes VI minus 2 VI. So ultimately it becomes VI minus 2 VI is 1 VI, right? Minus 1 VI minus into minus. So that goes on, it becomes plus. So R6 by R4 into VI. So that's my total output voltage. Right? So please make note of this. Output voltage is R6 by R4 divided by VI. Now during the negative cycle, what happens? So during the negative half cycle, VA is equal to minus VI. So VA is the negative cycle, right? And it should be inverted, but then here 2 times is not happening. The same inversion is happening. Okay. And VB will be equal to 0. So what is going to be our output voltage? Our final output voltage is going to be as usual minus R6 by R4, okay, and minus Vi plus 0. So which means it's going to be R6 by R4 into Vi. So whatever is your input that is being influenced, it comes at the output side. So the output is full wave rectified version, which means there is a rectification happening at the positive cycle, rectification happening at the negative cycle also, right? So with the positive cycle, you can see that 2 times of Vi is coming, and with the negative cycle also, the inversion is happening. Okay. And the other thing that we can concentrate here is the circuit has overall gain of 1. Okay, so that's important. When R6 is greater than R4, now let's take this condition. Whenever R6 is greater than R4 and R5, okay, 4 and 5, amplification and rectification occur 4. So always keep in mind this feedback resistance should be a little greater. If it is greater, then only amplification. If it's not greater, amplification wouldn't happen. Okay, so it can be either for summing circuit or it can be for precision circuit. Okay. Okay. A precision full wave rectifier is also known as absolute value circuit. Why is it called absolute value? Because it is playing with, or it is being able to modify the positive cycle and the negative cycle as well. Okay, this means the circuit output is absolute value of input peak voltage regardless of input polarity. So we are able to change the properties of my input waveform based on how I connect the diodes and based on how these resistances are designed, right? So in our upcoming classes, right, we will look into a few more concepts like solving a problem, and we will also see how it is designed in the computer, and we are able to see the same type of waveforms, right? So we will catch up in our upcoming classes with these concepts.